2, 1, happy return. So when is a function non-differentiable? So if you're going to define the derivative, so here it is, that is something that you should be kind of familiar with before watching this video. So I did the introductory to the derivative. I'll put a link up above there. Now, once you grasp that concept, so it's basically just a function which is nothing else but simply the slope of the tangent at any point on the curve. So, or at least wherever the function is differentiable. So now I want to talk about in this video what happens when the function is not differentiable. So when does this limit actually not exist? Okay, so this non-differentiability at a particular point is interesting, and it's important to know because not every function is going to have a derivative at every single point, and we have to be aware of that. So there are kind of two things that you should think about. So first of all, so number one, a function cannot be differentiable at a particular point if it is not continuous at that point. So that's number one. So it has to be continuous, okay? So that's the thing. So continuity, okay, at, let's say x is equal to a, must be met. And if it is not met, so if it is discontinuous, so if it's discontinuous, it could be, you know, 3 different types of discontinuities. It could be a jump discontinuity. It could be an infinite discontinuity. And it could be even the tricky one, which is the removable discontinuity. Now, the interesting part is that the limit for the removable discontinuity, it can exist, right? But because it is not continuous at that point, therefore it's discontinuous, and we would not be able to find the derivative at that point. Now, for this, for the discontinuity concept, if you've missed it, if you forgot it, put up a link up above there for you. If you're comfortable with it, great. So that's the first test. Now, what this actually tells us is that before we start doing any kind of differentiation, we should know where the function is continuous. So we should kind of know what the domain is of that function, and is it continuous on that particular domain, okay? So throughout. So that's the thing. So is it definable? Okay, so now that's number one. Number two, okay, what we want to watch out for is we do want to watch out for that, okay, if it is continuous at that particular point, then we also have to make sure that this limit actually exists. And when we say that a limit exists, that means it exists both from the left-hand side and from the right-hand side. So very often we can go ahead, okay, and try to find what that limit is, but we do have to be careful, okay, if it does exist. So now I want to give you a few kind of instances. When would it not exist? So we said it has to be continuous, but what if it is continuous? Can it happen that this limit right here would not hold? And yes, it can happen. So I'm going to give you, several examples that we're going to go over and things that we should watch out for. So I'll give you a very simple example here. So here is the absolute value function. Now, the absolute value function is actually defined for all x, okay, being real numbers. So it's defined for the entire domain of x, okay, being the real numbers. Now, this function you may remember, so the absolute value, so if you would graph it out, so if this is your y-axis, okay, this is your x-axis right here, this, okay, is nothing else but simply, okay, a line, okay, to the left of 0, and then a line to the right of 0. So here, this is, f1 at x on this side is just equal to x. And then on the opposite side, f1, okay, of x is actually equal to negative x. So if you would substitute it in, that negative would cancel the negative that you're substituting, and it would always be positive. So the absolute value is this. Now, what's interesting is what happens here at 0. Now, for outside of 0, so for everywhere that we have x, okay, which is not equal to 0, then this function, so f, okay, so the function, so the derivative of the function does actually exist, because it's just nothing else but a line, and we can find it, okay, we'll go over that. But I want to concentrate on this point 0. The function is defined at 0, so it is continuous at 0, so that means the limit, okay, as x is approaching to 0 exists for us, so that's great. But we will run into a problem when we're trying to find this right here. So I'm going to copy this, okay, and I'm going to bring it down right here. I'm going to kind of shift it over, make it smaller. And now look what's going to happen. Visually, you can probably tell as we're getting closer and closer. So as we're getting closer to here, okay, so it looks like the slope, okay, is equal to -1 on this side. But as we get closer and closer and closer here, the slope on the right-hand side is equal to 1. So the slopes are not equivalent, right? So the slopes from the right and the left are not equivalent. And indeed, that is true. So in order to work with this function, so now what I can do is, okay, I'm going to take a look and find this limit. Now, the limit as h, okay, is approaching 0, I guess, from the left-hand side. So that means for negative values of h. So this is what I would get. I can substitute this whole thing in here. So I'm going to get negative, this is going to be x, okay, plus h, minus, I guess this is going to be negative, so again, negative x, like so, and then over h. All right, so bringing all of this in, right there, you'll notice that the x's will cancel, so negative x minus h plus x all over h. This cancels out, and then what I'm going to get is negative h over h, and so this cancels, and I'll just get -1, and the limit as h is approaching from the left-hand side right here, so this is going to be just -1. Now, if I did the same thing, and I would encourage you to try it, so as h is approaching from the right-hand side, right here, so this would have been x plus h minus x all over h, and if you do the manipulation, all right, you'll notice that I'm going to get 1. So notice the limit from the left and the limit from the right are not equal to each other. So there's like an abrupt change. It's almost like there's like a cusp of somehow right there at that 0. So this function is actually not differentiable at 0, right? So there is no derivative at 0, and that should kind of make sense to you, because if we had a cusp like this, right? Maybe let me draw it, properly. So if it's like that, and I wanted to try to find a tangent at that point, I mean, this could be a tangent at that point. This could be a tangent at that point. Could be even a flat line can be a tangent. So I can find a lot of different tangents, right? So just because I have that little cusp there, there is not one tangent that fits. From the left-hand side, we know that the one that will fit is this one. From the right-hand side, we know that the one that will fit will be that one. So that's the one that I would have. But those are not equal to each other. And when that happens, well, this overall limit does not exist. So we would say that this function is non-differentiable at x is equal to 0. It is differentiable at any other point. So if I go on the left-hand side of 0, so anywhere, okay, if I pick any point on this side, then the function is just equal to this. And if I pick any point on the right-hand side, then the function is just that. And that is differentiable. and we can find that. So it is continuous, but not differentiable. So that's one example that you would have. Here's another example right here. And within here, so what I would want to be able to see is, what is the derivative? And here I'm going to say, okay, at 1. You know, does this equal to something? Does it exist? Now, I purposely have set this up. This case, what happens is that, so notice in the numerator, so this is nothing else. So this is a difference of square. So this is x minus 1 multiplied by x plus 1. And then in the denominator, I have x minus 1. Now, this tells me that x cannot be equal to 1. So it's not continuous at 1. Now, if I worked this out for any other value other than 1, sure, this would cancel off right here. Oh, I'm sorry. Okay, so this one would cancel. Okay, so this and this would cancel. And I would have that the function is just simply equivalent to x plus 1, which is nothing else but a line. So if I graph this out for this function, so x, and so let's say this is my f2 of x. So this is 4, so let's say this was 0, this was negative 1, this is 1. So this function, so basically crosses through 1, so it looks something like this, all right? So it carries off. However, at this point, it has a removable discontinuity. It's not defined there. We cannot set as x is equal to 1 because we're going to get a problem in here, right? So we run into a problem. So this is actually a removable discontinuity. So we do not even have to check this limit. So if somebody's asking us for what is the derivative at 1, and sometimes you might abbreviate it like this, by the way. And also if you want to find out what this is x is equal to 1. You want to find the derivative, okay, at x is equal to 1. So that's another notation. It's the same notation as this. But it has a removable discontinuity. So we have a problem right there. And for that, okay, it cannot be differentiable at that point. So that's another example. So it's just simply not continuous. So it fails. This right here, it has a removable discontinuity. You can stop right there. The first example, it was continuous, so we had to check if this limit existed, and it had a little cusp, okay, and that was a problem. Now here's another item, okay, so here's another function. This is a piecewise function, so it's made up of 2 pieces right here. And for this, so once again, if I wanted to find, let's say, what is this is, okay, let's find the derivative of this function, and let's try to find it. This is, I guess, it would be for 1. So the first thing that we have to check is, you know, is it continuous there? You know, so we can actually check continuity, right? So, well, is it defined? Yes, it is defined. So if I set f at 1, okay, so f3 at 1, I would simply get, so this would, I would have substituted 1, so negative 1 plus 1, so it would have been 0, so it's defined, okay, there. Does the limit, right, exist? So we need to know that. Does the limit, okay, as x is tending towards 1 of this function, right, does it exist? And that's something that we did discuss in actually limits and several examples, okay, for that. So I can substitute it in, okay, and then I can find if that limit exists or not. So that would be, again, so from the right-hand side, I would have to find it, from the left-hand side, and this limit does exist. You can check for yourself, and it is actually equal to 0. So the function's continuous, right? So it does satisfy continuity at that point. But if I now try to find the actual So by definition here, so let me steal this again. So if I try to find, because that's how the derivative is defined, so if I copy this and I bring it down right here, so for this, well, we're trying to find it. So here at 1, we can substitute it. So right there, does that limit exist? You can check for yourself that the limit actually will not exist. And let me graph it so you can do it from the left and the right hand side. So whenever you have a piecewise function, okay, within here, whoops, okay, let me bring it down, cut it, it's right here. So whenever we have a piecewise function, and notice that this function, so here, so we have a separation, okay, somewhere here, so for x being defined, on the right hand side of 1 and then on the left hand side of 1. So when that happens and you're kind of at that intersecting point, okay, of that piecewise function, always be careful at those points. So this function is differentiable everywhere except at that particular point. And let me show you. So once again, so if I bring out Desmos here, I'm going to try to put it on the side. So this function, so f3 I'm going to call it, is equal to, so now we have, this is for x less than or equal to 1, okay, the double dot, so negative x plus 1, comma, and then for x is greater than 1, double dot, so x minus 1 squared, let's put that in there. So there you have it, so that's how it looks like. And then if we zoom in here, right, so you'll notice, okay, as we zoom in here, on the left hand side it looks like the derivative, the slope, because the slope on the left hand side is nothing else but a line, so it looks like it's negative 1. So the slope on the left of this, so on the left of that, it looks like it's going to be negative 1. And you can check that. You can substitute it in and then find out what that is. And then the limit, if we let h approach from the right-hand side, from that, so this we would have been coming along this direction, what the slope is. Well, the slope in here is actually going to be 0. It's going to tend towards 0 because this is a quadratic, okay? So this is going to be tending towards 0, and then it jumps over. So that is pretty cool, okay, to be able to see that. Now, I would encourage you to try it, to find out the limits, and then you'll see that the left hand and the right hand limits of your derivative will not be equal. Now, what's neat is that we, okay, so in dx, so if you write d over dx, and then you put your function in, you will actually be able to find, okay, what the actual slope is. So here, let me just show you. Okay, so this actually plots the actual derivative for us. And notice indeed, so we have, so this is the slope to the left, okay, is all fine. So we can go all the way down, okay, in here, and we can find it. But then, okay, the slope over here, okay, is something different. So notice the left and the right hand side slopes are not equal to each other. And I would encourage you to check that out, okay? It would have been pretty neat. So on the left hand side, you'll find that the slope is negative 1. On the right hand side, if you do the limit, you'll find that the slope is actually 2x. All right, and 2x, which means at 0, would have been just 0. All right, so these are just some examples and things to keep in mind when functions are not differentiable at a particular point. So that is what I wanted to talk about in this video. Okay, I hope you found it useful. We'll see you in future videos. Bye, everybody.